Okay, so today what we're going to do is we're going to start out with our familiar sum and difference formulas from the last session, and then we're going to move into how we create what are called double angle formulas, and then we will use those double angle formulas in the second segment to create what are called half angle formulas. And the good news is, well, the bad news is you need to know your sum formulas, sum and difference formulas, by heart. Okay, just like knowing the Pythagorean theorem or knowing the quadratic formula. So in trigonometry, we want you to know the sum and difference formulas. It should be easy then for you to remember these double angle formulas. So those are things I'd like you to commit to memory. But then when we create these half angle formulas, we don't use those very often. So just, you need to know how to use them, but you can just look them up when you need to. So as far as testing goes, we're not going to ask you to pull those out of your hat, okay? And then we want to practice in the third segment how to actually use these formulas. So I have a variety of problems I'd like to go through today, right out of the textbook, that that'll help you sort of see how to appropriately do these problems. So let's start here with our sum formulas that we're familiar with, and then create these double angle formulas. And I might even do a sample problem or so, but I want to just refresh our memories first on what these formulas are. So if we have the sine of the sum of two angles, then I talked in the last session about how to remember those things. With the sine formula, for the sum or difference of angles, you'd start with the product of the sine of the first, cosine of the second. And then plus the opposite combination. So then the cosine of the first times the sine of the second. And here we're using the Greek letters, which we call, what's this one? Alpha. And that one? Beta. Alpha and beta. Similarly, the cosine sum formula for the cosine of the sum of two angles starts with, the way to memorize it is it starts with the products of the cosines. So the cosine of the first, cosine of the second, and then the opposite plus or minus character. So in this case, since I'm adding the angles, it's going to be the difference here. And then followed by the products of the sines. Notice from the last session, I never mentioned a tangent formula for the sum or difference. But if I was doing that, all I would have to do, the reason I don't ever hardly mention it in class, is because all you have to do is take your sine formula and divide it by the cosine formula to create the tangent. So you're going to have essentially a big fraction here of this expression divided by this expression to create the tangent of the sum of those angles. There are 4 different items in these formulas, aren't there? Sine and cosine of each angle, of the two angles, right? So there's 4 different items. Each of those items are a ratio. Each of those items are a ratio. Okay? All you have to do is figure out what those ratio values are, and they're usually going to be fractions, and you just drop them in here. Fraction times a fraction plus another pair of fractions multiplied together, and similarly down below if you're doing a tangent. Okay? So there's a summary of the formulas. So here's a problem. Let's see if we can do this. This one comes from, in our book, number 35 on page 474, and it says, you're given the sine of alpha is 5/13. Sine of alpha is 5/13. And they also tell us where alpha sits. Because if we said sine of alpha is 5/13, being a positive value, what quadrants can angle alpha be in if the sine is positive? 5/13. First quadrant or second quadrant, right? And what I'm thinking is I'm thinking my unit circle, and my sine readings are my y readings on the unit circle. So quadrant 1 or quadrant 2. Now they tell us some information about alpha in the book. They say that angle alpha is between minus 3 pi over 2 and minus pi over 2. So minus 3 pi over 2 is going to be clear back around here, right? Terminal side right there. And minus pi is going to be back over here. So angle alpha is trapped up in here, And that sine reading is 5/13. So it's going to be something like this. The terminal side is going to sit here, and that reading is going to be 5/13 right there. So I usually don't draw a big fancy picture like this with this piece of information. What I would draw is this. I draw the initial side, and by looking at this information, I would draw an angle like this. And then I would show either 5/13 on the y leg on my unit circle of radius 1, like we have here, or I would simply think of this as y over r, 5/13. If you have a hypotenuse of 13 and one of the legs of the right triangle being 5, then the other leg yields a Pythagorean triple, like a 3, 4, 5. What's this one? Isn't it 13 squared minus 25? Hypotenuse squared minus leg squared is this leg under the square root then? So it's 12. Turns out to be 144. Square root is 12. But look at the direction of it. You have to assign a negative. Be very careful there. Assign a negative to that. So here's a picture of alpha. Here's a picture of angle alpha with the y, the x, and the r. That's the first piece of information that's given to us. The other piece that's given to us is about another angle they call beta, and they tell us that the tangent of beta happens to be square root of 3. Now that goes back to a unit circle item. What would that angle be? Beta. 60 degrees. Here, I'm keep taking you back to fundamentals. If you're up here at 60 degrees, the slope of that terminal side right there is square root of 3. The tangent of beta, that could be your beta angle right there. It also could be down here, couldn't it, in that third quadrant, same tangent value. If you were at 30 degrees instead, what would be its tangent value? If you were at 30 degrees, that's not going to be what we have in this problem. That would be 1 over square root of 3 for the tangent reading. Okay, just a couple familiar numbers. You don't have to memorize that, but it's not bad to know it because it shows up in a lot of problems. So we're not using this. Everybody with me so far? Yes?
Is there a reason why the negative pi over 2 is at pi and not pi over 2? Is that just because it said...
I'm sorry. I wrote that wrong on the board. Thank you for catching that. You folks are responsible for catching my mistakes, okay? Okay, so that I don't get a bad recording out of this, okay? So that should be pi right there. Thank you. So we're trapping between minus 270 degrees effectively, right? Which I showed initially, and minus pi or minus 180 degrees. And that was not a pi over 2. Thanks. Any other mistakes up here? Okay. Now, back to this. They tell us that, and I did make a mistake with what's in the book. The tangent of beta in this problem was not square root of 3. I couldn't read my notes. It's negative square root of 3. So, it's not sitting in the first or third quadrants. Since that tangent is negative, it has to be sitting in the second quadrant, doesn't it? Or the fourth quadrant for a negative tangent reading. All right, and they tell us that beta, this angle beta, is trapped between pi over 2 and pi. So here's the correct place for that angle beta to sit. And here's angle beta right there. So what I normally would draw is not my unit circle. I'm just using that to help you recall something here. But what I would end up drawing is I would draw the initial side, and I would draw myself an angle sitting up here in the second quadrant with a tangent reading of, I could label it a variety of ways. This could be a square root of 3 positive y leg, and I'd have to assign a what here to get this tangent reading? A -1. And the hypotenuse, be careful, square this is 3, and subtract from it the square of -1, which is 1. It's 2, isn't it? So I think it should be square root of 2, is that right? Or is that right or wrong? 3 minus 1 is 2, square root of 2 on that leg. That's strange, isn't it? That can't be right. So what did I do wrong? I'm having a rough day. I'm supposed to add, right? How many of you believe my story? Good catch, Alyssa. Okay. Square root of 2 can't be longer than square root of 3. Okay. So this is a leg, so that's going to be 3 plus 1 is 4, square root of 4 is 2. Now that looks better, doesn't it? Because think of the ratios you'd get out of this for the sine of beta. Square root of 3 over 2. 120 degrees, 120 degrees. Okay? Or the cosine being -1/2. Nice familiar numbers then. Okay. So we got that pinned down, we've got this one pinned down, and then we haven't even gotten to the question yet. The question was asking, so this is what I would suggest you have in your homework, this kind of stuff, these little sketches like that. And then the question's asking, find a variety of things. Find the sum of alpha, the sine of alpha plus beta. Well, if you have these triangles drawn, then you take this formula that you've got memorized, and you're going to have sine alpha cos beta plus cos alpha sine beta. And now all you do is you just look at your triangles here and write down your ratios. So the sine of this angle alpha, here's alpha. The sine of it is y over r, 5/13, a ratio. The cosine of beta, you look at the picture over there, is -1/2. We're adding to it the cosine of alpha back here, -12/13. And the cosine, the sine of beta over there, square root of 3 over 2. And what we get coming out the door on that is -5 minus 12. Well, actually, this reduces right here, doesn't it? The 2 into the 12. Might as well reduce it. 2 up into 12, 6 times. 6 square root of 3 over 13, over the common 13. Any questions on that?
On the first fractions there, don't you have to times 13 by 2 on the bottom to get 26?
Thank you. I was hoping somebody'd catch that. This is arithmetic.
Yeah.
The common denominator here is 26.
And then you want to keep 26 so that you can add them together because it has an LCD at 26.
And so the common denominator...
-17 square root of 3 over 26.
Perfect. So -5 minus 12 square root of 3 over the common 26, because that's a more convenient way to write the result.
I'm a fucking retard. I'm lucky when I get it right.
Okay, are we good?
Yeah, I'm good.
Okay.
Or should we keep -5 and -12 apart or combine them?
Oh, what do you want to get there?
-17.
Oh, that'd be nice if there was no radical 3.
Because that's attached to it.
That's attached.
Yeah,
Big time.
capiche.
Big time. Okay, good. Now we're even. You caught me and I just caught you. Okay. Okay. Now, how about let's go down underneath here and do the cosine. Okay? Everybody with me? So I'm going to leave a little space down at the bottom here because I'm going to put the cosine formula for that alpha plus beta way down below here. And right above here, it starts with products of cosine. So I'm going to have the cosine of the alpha, the cosine of the beta. And then I'm going to change the plus or minus thing to minus, subtracting. And then we're going to have the sine of alpha and the sine of beta. And then right up underneath this arithmetic, I'm going to put these four ratios. Why am I setting it up this way? So I can get the tangent. So I can lead towards the tangent without having to redo a whole bunch of stuff and use up another whole board. So I look again at my triangle, and actually I don't even have to look back at my triangles again, do I? Because those ratios are all sitting right here, are they not? So all I'm doing is I'm looking for my cosine alpha reading, which is minus 12/13. The cosine beta is right here, minus 1/2. Minus, subtracting, the sine of alpha is 5/13. And the sine of beta is radical 3/2. And so then, cleaning that up without making a mistake on this, the common denominator is 26. And the numerator is a positive 12 and a minus 5 radical 3. If I'm then figuring out, everybody with me on the ratios? Okay. The kind of mistake we see people make all the time in trigonometry, and it's purely garbage, is we'll see people write down the sine of 5/13. That makes no sense. The sine of 5/13. Alpha is the angle. The sine of the angle is 5/13. So all we're ending up with here is a sum of sum and product combination of four ratios here. So there's the sine of the sum of the angles. And down below here we have the cosine of the sum of the angles in exact form. And then if we want the tangent, the ratio of this sine and cosine is going to then be our tangent of the alpha plus beta. So if you're careful with your arithmetic, you then have this complex fraction that is created here of this big fraction in the numerator, this big fraction in the denominator, and then we combine those by simplifying a little bit. I'd multiply top and bottom by what here?
The reciprocal of the denominator.
Well, that's true, or simply multiply numerator and denominator by the common denominator, 26, top and bottom. Gets rid of the 26.
Okay.
Okay? And so we're left then for that tangent reading with negative 5 minus 12 square root of 3 divided by 12 minus 5 square root of 3. Now, I'm going to just leave the answer that way. Oftentimes we would want to rationalize that denominator, but I'm not going to worry about it at this point. Alyssa?
You don't want to simplify when you're multiplying them out, do you? Because I simplified 12 over 26.
Right here, but keep in mind that 26 is also under this. Did you write minus 5/26?
I did the fractions separately first before I put them together and reduced the negative 12 over 13 times negative 1/2 on the bottom.
Right here?
Yeah, and then reduce that.
And you clean it, reduced it? Yeah, if you reduce it, you're not going to end up with a common denominator here, which is what we pointed out earlier. So it's probably preferred to do it like I've shown it here. because of that common denominator, which allows the simplification to occur. Do you see how 90% of this is arithmetic? And then, well, maybe not 90%, but there's a whole lot of arithmetic in there. You've got to be very careful with it. What if you were doing the problem for the difference in the angles? Instead, all three of these ratios. The sine of the difference of the angles, alpha minus beta. The cosine of the difference in the angles, alpha minus beta. And the tangent of the difference. Not too tough, is it? All we'd have to do is come back in here and come back up to your formulas at the top here. If you're dealing with the sine of the difference in the angles, it's going to be the same formula with a negative sign tagged in there. If you're doing the cosine of the difference in the angles, it's going to change to a positive right there. And then you can just track that right along down through this problem. So this negative will become a what? That's going to become, see that negative negative there? That's going to become a positive. Let me move this up. I'm mixed up with my markers here. That was a minus there. So that's going to become in red a plus. And then down below here, that minus right there becomes a plus. Tracking. And then over here, this would become the difference in the angles, and so that's going to become a plus, and that's going to become a plus on those terms. So you can save yourself some time if you're careful tracking those plus and minus characters, addition or subtraction terms, and then just build the structure like this. I could take the time to check this on the calculator, and we could end up getting the result. Now the trouble is the inverses, to come up with these angles and store them in the calculator, you got to be very careful, and so that's actually a little more sophisticated because we have to go back to thinking about our inverse functions to check this on the calculator.
Are you allowed to leave the radical on the bottom of the tangent?
Normally you would rationalize that, but I just wanted to get to this point with you. And the important part is to be able to track through this part. Mm-hmm.
But on the test, like if we're doing when we're doing.
I'm not going to give you one this complex. I will give you something like this, though. Well, actually, I'll give you something I might ask you to figure out one of these things. Okay. All right. Because we want you to know the fundamentals. Okay, that's a pretty good one. Now, here's another one for you before we go on to the next segment here. Another question coming out of the book on page 474, number 53. It says verify. Now these are the kind Tim likes, right? Verify these identities, okay? And here we have the sine of 3 pi over 2 plus theta. Show that that is the same as minus cosine theta. Draw a line down where the equal sign is what I've suggested. And our objective is to end up with what right down here? At the bottom. A smiling face. Okay, that's our objective. Okay. So, play the game. Got it in your brain now, the formula? Sine of the first angle times the cosine of the second plus the cosine of the first, sine of the second. Joshua?
Would we be able to use the property we talked about last week where...
Yeah, hold off.
Okay.
That's the quick and dirty way to get it, okay? But we'll do that in a second. Thanks for noticing that. The sine of 3 pi over 2, I'm thinking unit circle, I'm down here at this location right there with my terminal side, aren't I? And the sine reading is -1 at 3 pi over 2. So that ratio is a -1 right there times cosine theta. And then the cosine of 3 pi over 2 right here is 0, isn't it? The cosine reading of that terminal side is 0 plus 0 times the sine of theta. And so there we have negative cosine theta is equal to the cosine theta on the other side, and we're feeling good. Okay. What Joshua was getting at a moment ago was the thing I showed you the other day, is you take and build yourself a dummy angle. I usually take a small acute angle in the first quadrant on my unit circle. So there's angle theta, and so there's the sine of theta, and here's the cosine of theta. Simple, acute, small, acute dummy angle, sample angle. And then all I do is I add multiple of 90 degrees here. 3 times 90 is 270. So I add 270 to this angle, and it brings me clear around to here. And I end up with this lower triangle. That y reading here, this is getting kind of messy. The y reading right there is the sine of that angle, 3 pi over 2 added to theta. And that short leg here between my fingers is the cosine of that big angle. This whole big angle, theta plus the 3 pi over 2. So there's the cosine of theta plus 3 pi over 2. And you look at this triangle, those two triangles are identical in shape. Okay? And so that means that that leg, uh-oh, something's wrong. The sine, oh, I'm sorry, yeah. I was a little nervous there for a second. Hate to be nervous in front of a camera, okay. So here we have the sine of 3 pi over 2 plus theta, right? Notice that that's the same length as the long leg here, isn't it? Aren't they? But what's the distinction between the two? Yeah, the one where my fingers are right now is negative, isn't it? And this reading right here is positive, but they're the same length. So if I assign a negative to this cosine reading here, that's equivalent to this value. Okay, so that's a little refresher of this little thing I showed you back when I first started talking about sum and differences in a previous session, is you can use a dummy angle like this if you're dealing with multiples of 3 pi over 2, or excuse me, pi over 2 multiples added or subtracted from your angle. Okay, this is the nice, clean, algebraic way to work your way into it. Okay, yeah.
In our homework, would you rather us show it as the proof or the picture?
If it says verify, then this is the approach you want to use. Okay. But that little tool over there is going to be very handy in checking yourself. Okay. Let's go ahead and end this segment, and then we're going to go ahead and move on to this transition from double angle formulas, or to get to the double angle formulas from the sum and difference one. No, actually, I never even got to that, did I? I'll get to them here in a second.